Hello everyone, welcome to our presentation. Today we'll use quantum mechanics to clearly explain how ionic and covalent bonds actually form.
Chemical bonding is the reason molecules even exist. Every structure we see in chemistry, from water to DNA, depends on how atoms bond with each other. The way atoms bond determines the shape of molecules, how strong they are, how they react, and even how stable they are over time. For example, the difference between a gas and a solid often comes down to the type of bonding involved. Without chemical bonds, we would not have matter in organized forms, and chemistry as a science would not exist. So understanding bonding is really about understanding the foundation of the physical and biological world.
Classical models versus quantum mechanics. The limits of classical models is the octet rule, which predicts bonding patterns but not why bonds form. This fails for BF3, SF6, NO, and other transition metals. With Coulomb's law, we treat electrons as point charges, which explains ionic attraction but not covalent bonds, bond lengths, or molecular geometry. Why we need quantum mechanics. Quantum mechanics helps explain electrons as wave functions, not particles. Bonding happens when wave functions overlap in lower energy by increasing electron density between nuclei. Quantum mechanics explains true bond origins, bond strength, bond length, and molecular shape, things that classical models cannot.
What is quantum mechanics? Electrons as wave functions, also known as psi, are not classical particles, but the wave function contains all the information that is meant for the electron. We will never see the wave functions directly, so people will always use psi squared instead. The electron does not have a single exact location until you measure it, as it exists as a probability cloud spread out in space. This is why atomic orbitals such as s, p, and d are shaped like clouds. They show where the electron is likely to be, not on a pattern that it moves on.
When we talk about covalent bonding, we're really talking about what happens when atomic orbitals from different atoms start to overlap. In quantum mechanics, these orbitals aren't just little shells around a nucleus. They're actually wave functions which have mathematical descriptions of what an electron is supposed to be or likely to be. Electron wave functions can interfere with each other. They can either interfere constructively, where their wave functions add together, or deconstructively, where they cancel out. When the overlap between two atoms' atomic orbitals lead to a constructive interference, the result is a bonding molecular orbital. This new orbital has an increased electron density between the two nuclei, and that shared electron density stabilizes the atom and forms a covalent bond. So on a quantum mechanics perspective, a covalent bond isn't just two atoms sharing electrons. It's the formation of a lower energy molecular orbital created by constructive combinations of their electron wave functions.
The hydrogen molecule is the simplest example of covalent bonding, but it clearly shows how quantum mechanics works in bonding. Each hydrogen atom has a single 1s orbital. When two hydrogen atoms come together, these orbitals overlap and combine to form two molecular orbitals. One is the bonding orbital, called the sigma, and the other is the anti-bonding orbital, called the sigma star. The bonding orbital has lower energy and places electron density between two nuclei, which stabilizes the molecule. Electrons always fill the lowest energy orbital first, so both electrons stay in the bonding orbital, which allows the molecule to form. The Pauli exclusion principle also applies here, meaning only two electrons can occupy that orbital and they must have opposite spins. This explains not only why the hydrogen molecule is stable, but also why it can hold two electrons in its bond.
Heitler-London model and modern quantum view. Our bonding from wave function combination is the Heitler model for H2 that shows the bonding occurs when the two atomic wave functions combine, which is our equation given. This symmetric combination increases electron density between the nuclei. Our density redistribution is when electrons delocalize, the density shifts into the internuclear region. This redistribution is a true quantum mechanical origin of a covalent bond. Modern MO theory builds on this with bonding and anti-bonding orbitals formed from wave function interactions. Covalent bonding arises from wave function overlap and electron density concentrating between atoms.
Ionic bonding. Electron transfers ions and lattice formation, which in other words is an ionic bonding. One atom, usually a metal one, loses an electron, and another atom, usually a nonmetal, gains that electron.
Hydrogen bonding is often shown as a weak attraction between a hydrogen atom and an electronegative atom like oxygen or nitrogen, but quantum mechanics reveals that it is more complex than that. In reality, a hydrogen bond involves a small amount of orbital lap. A lone pair on one atom interacts with the anti-bonding orbital of a nearby bond. This gives hydrogen bonding some covalent character instead of being a purely electrostatic force. This explains why hydrogen bonds are directional and why they are stronger than expected from a simple charge attraction alone. Hydrogen bonding is extremely important in real systems. It explains why water has a high boiling point, why proteins fold into specific shapes, and why DNA strands can pair and hold together reliably.
This slideshow, we have learned that quantum mechanics as the foundation of chemical bonding Classical models describe bonding patterns but cannot explain bond strength, geometry, or electron behavior. Quantum mechanics treats electrons as wave functions, and bonding comes from their overlap, interference, and density redistributions. Covalent, ionic, and hydrogen bonds all follow the same quantum mechanic principles of orbital interactions and energy minimization. From simple molecules like H2 to larger, more complex systems, quantum mechanics explains molecular structure, stability, and reactivity at the most fundamental level. Quantum mechanics reveals the true mechanism behind all chemical bondings.
We would now like to introduce Dr. Hrant Hratchian, our Vice Provost and Graduate Dean of Natural Sciences. We will hear from a physical chemist about the importance of quantum chemistry and computational chemistry.
From your perspective, what is the most important thing quantum mechanics explain about chemical bonding that classical models cannot?
Well, there's a lot about chemistry and physics that quantum mechanics is essential for explaining, but maybe one of the most widely impactful sort of consequences in terms of chemical bonding that I can think of offhand would be the description of electron delocalization and its impact on, for instance, conjugation and aromaticity, and trying to understand a uniform way to think about electrons as engaging in sort of delocalized bonding structure. There's a lot of impact in the way we think and rationalize reactivity and properties, and just chemical behavior in general, especially in organic and inorganic chemistry, that relies on our sort of conceptualization of a delocalized electronic structure, which is at its core a quantum mechanical result.